Welcome everyone to today's Explainer. We're diving into something today that, honestly, feels like it was ripped straight out of a sci-fi movie. Just imagine for a second, typing a text message to a friend, or drafting an entire email, and you're not using your hands. You aren't even speaking out loud. You are literally just thinking. And here's the kicker. You're doing all of this without a single surgical incision in your head. Well, today we are unpacking Meta's absolutely mind-blowing new research on a piece of tech called Brain2Qwerty. This is their version 2, and it's designed to decode human thoughts directly into text using completely non-invasive technology. It's a massive, massive leap forward for brain-computer interfaces, and the implications here are just staggering.
Okay, so here's our roadmap for the Explainer. First, we'll look at the Human Communication Challenge. Then, we'll introduce Brain2Qwerty version 2. Third, we'll pop the hood and see how this decoding actually works. Fourth, we'll measure its breakthrough performance. And finally, number 5, we'll map out the path to getting this into actual clinics. Let's dive right in.
Section 1. The Human Communication Challenge.
You know, we have to ground this in why it actually matters. Every single year, thousands of people around the world are abruptly stripped of their ability to communicate. We're talking about the aftermath of severe strokes, traumatic accidents, or really devastating brain disorders. The result? A profound, terrifying isolation. Imagine having a completely active, sharp mind, but you're trapped inside a body that just won't let you express your thoughts or your needs or tell your family you love them. Finding a reliable way to restore that communication, it's not just some fun technical puzzle. It is an absolutely urgent, life-altering necessity for so many people.
But right now, there's a pretty stark contrast between the current solutions and where we actually want to be. Up until recently, restoring speech for severely paralyzed folks meant relying on brain implants. Now, these neuroprostheses are incredible pieces of engineering, but they come with a huge catch. They literally require invasive, open brain surgery to physically place sensors right onto the motor cortex. It's risky, it's incredibly expensive, and it just isn't an option for everyone. But the ultimate goal, the holy grail of this entire field, is non-invasive, surgery-free decoding. Imagine getting that same high-fidelity signal you'd get from a brain implant, but doing it entirely from the outside looking in.
Section 2. Enter Brain2Qwerty version 2.
So let me formally introduce you to the star of the show, Brain2Qwerty version 2. This is an AI model specifically built to decode natural sentences directly from non-invasive magnetoencephalography recordings. We just call that MEG for short. So what is MEG? It's basically a neuroimaging technique that maps out your brain activity by picking up on the tiny magnetic fields produced by the natural electrical currents running through your brain. The absolute key word here is non-invasive. A person just sits in an MEG scanner. There are no scalpels, no implants, no recovery time. The system just listens to the brain's activity to figure out what they are trying to type.
Section 3. How the decoding works.
Now, to really appreciate the genius of version 2, we kind of have to look back at last year's version 1. Brain2Qwerty version 1 was a massive proof of concept. It was even accepted in Nature Neuroscience, but it had a really clunky limitation. It required the precise timing of every single keystroke. It needed to know exactly when you were thinking of pressing A and exactly when you pressed B. Because of that, it couldn't work in a natural, fluid way. But version 2, it completely shatters that bottleneck. It now generates sentences directly from a continuous flow of brain activity. You just think, the scanner records the continuous stream and the AI translates it. It's a monumental shift toward how we naturally communicate.
So how does it handle that continuous flow of data? Well, it actually acts a lot like the human brain does when we read. It uses 3 hierarchical modules. First, it decodes things down at the letter level. Then, it scales up a bit to decode at the word level. And finally, it decodes the overall structure at the sentence level. And this is so brilliant because it illustrates how the AI builds its understanding piece by piece. These aren't isolated little steps. The modules work together simultaneously to jointly improve the final output. Think about it. If a letter is a little ambiguous, the context of the word helps fix it. And if a word seems out of place, the overall sentence context smooths it right out.
Section 4. Measuring the breakthrough performance.
Okay, so let's talk about the secret sauce behind version 2's massive leap in ability. It can pretty much be summed up by one number: 10 times. The researchers scaled up their training data dramatically. They went from analyzing about 2,200 typed sentences per participant in version 1 all the way up to roughly 22,000 sentences per participant in version 2. In the AI world, there's this concept called a scaling law. It basically means that the more high-quality data you feed a model, the better it gets at doing its job. And in this case, pushing that scaling law delivers some truly profound results.
Let's look at the average or mean performance across the healthy volunteers who took part in this study. In version 1, the mean word accuracy hovered right around 40%. Look, it was a great start, but definitely not reliable enough to hold a real conversation. But by unleashing that 10x data increase and using that continuous hierarchical architecture we talked about, Brain2Qwerty version 2 rocketed that mean word accuracy up to 61%. That is a massive, highly capable jump in average performance across the board. But, averages really only tell part of the story. Let's look at the absolute ceiling here, the best participant in the study. In version 1, the best accuracy anyone achieved was 48%. But in version 2, that peak capability skyrocketed to an incredible 78% word accuracy. So the crucial takeaway here is just how incredibly close we are getting to flawlessly translating human thought, all without ever physically touching the brain. I mean, hitting nearly 80% accuracy from an external scanner is just a breathtaking milestone. Let's see how this actually plays out in practice, because this is fascinating. So here is a true sentence a participant was actively thinking: will a new mountain range be forming underwater? Now, look at the AI's decoded attempts from 3 different subjects. Subject 7 gave us, will a new mountain range be formed underwater? I mean, that's fundamentally perfect, just a tiny grammatical shift. Subject 9 gave us, will a new mountain be coming underwater? Again, the core meaning is entirely intact. It captures the concept of a mountain, water, and something happening in the future. These slight imperfections are actually incredibly revealing. They prove that the AI isn't just mindlessly numerizing phrases, it is genuinely grasping the semantic meaning of the brain's activity and doing its absolute best to reconstruct that thought into text. Honestly, it feels deeply, deeply human.
Section 5. The Path to Clinics. Now, Meta's researchers are being incredibly transparent about the hurdles that are still left to clear. First off, while 78% is an amazing scientific achievement, it does still mean there are too many word-level and character-level errors for practical everyday use. Just imagine trying to send a quick text and having every 5th word be wrong. It would be super frustrating, right? To fix this, they need to keep pushing that scaling law. They need even larger datasets to train the AI so its performance doesn't just plateau. And secondly, the physical hardware is a huge bottleneck right now. The Meg device used for these recordings, it is not something you can just pop on your bedside table. It is a massive, highly specialized scanner that is completely inaccessible to the vast majority of patients who actually need it. But please, don't let those hurdles dampen your excitement, because there is massive hope on the horizon here. The hardware landscape is shifting rapidly. Meg sensors are continuously shrinking and improving, and we are actually already seeing the very early stages of wearable Meg technology. The long-term vision isn't about wheeling a patient into a giant room-sized scanner. It's about bringing a lightweight, wearable device directly to the patient. You combine that shrinking hardware with an AI that just keeps getting smarter the more data it eats, and you suddenly have a very clear roadmap to a viable clinical tool.
Which leaves us with a truly exciting thought to wrap up on. Meta is championing open science with this project. They are sharing their publications, their code, and their data with the entire global research community. So, with the brightest minds worldwide iterating on this non-invasive tech together, it really is no longer a question of if we can decode thoughts without surgery. The real question is, when will mind-reading wearables become an everyday medical reality? The pace of this innovation is just staggering, and I, for one, absolutely cannot wait to see what version 3 brings. Thank you so much for joining me for this explainer. Keep feeding your curiosity, and we'll catch you next time.